All right? Okay, so let's move on. So maximum likelihood estimation can be applied to non-Gaussian distributions. This is just one example that I am using a Bernoulli distribution. Okay, so by Bernoulli, I mean that there is an underlying parameter theta, and all your sample data points, xn, they are drawn from this Bernoulli distribution. It would be either 1 or 0 for this sample data point. The probability getting a 1 is theta, the probability getting a -1 is 0. Now, when will this happen? This will happen when you look at a problem like this. You have a graph, okay, and then you say that this is a Erdős-Rényi graph, and then there is an underlying probability of getting an edge, and so you will either get a yes edge or no edge, okay, and they are all equal. They are independently distributed. They're identically distributed across the entire network. Okay, so the presence or absence of the edge depends on this Bernoulli distribution. Then you ask, okay, what is the underlying parameter theta for this graph model? So you can run this kind of a study, and it turns out that you can also write down the likelihood function for this problem, and then the likelihood function will just become this Bernoulli equation. Now, the Bernoulli equation is a little bit different from the Gaussian. The Bernoulli likelihood is theta to the power xn times 1 minus theta to the power 1 minus xn. Why is this the case? Well, because xn is just binary, it's 1 or 0. You can put in is 0 or 1, right? So if you put in xn is 1, then this guy will be gone. You only have this theta. Otherwise, you put a 0 here, this guy will be gone. You only have this term, right? So the Bernoulli, this equation is giving you this binary switch between the two cases. If you have n of these samples, you can just write down the summation to the power. Okay, so you get this likelihood function. Take the negative log, you get this expression. So everything is written in terms of this summation and also the log theta, right? So the bottom line is that once I give you this definition of the likelihood, then writing down the negative likelihood, log likelihood is just a homework exercise. Okay, so you can follow the recipe and then do these. Now, the maximum likelihood estimate of this Bernoulli distribution can also be done fairly straightforwardly. You take the derivative with respect to theta, set it to 0, and then you do all these calculations, and then with some steps of the linear algebra, you can get to this final result, which very interestingly is the same as the Gaussian case. Okay, that just happens for quite a number of distributions where if you try to estimate the mean is indeed the sample mean. Okay, now it's not always the case. You can always create distributions that make this fail. Okay, but I would say normally for most of the distributions that you will encounter will have this. Okay, if you're interested, I can work with you on pathological cases to make this fail. Okay, so the point is that theta is not always equal to the sample mean if you try to estimate that. Okay, it can happen to have non-sample mean. Okay, so biased versus unbiased estimators. You can okay. So these two terms, they are called the empirical average or sample mean, or empirical covariance, called the sample covariance. The mean is unbiased because you can show that the expectation of mu hat will equal to mu for all n. And you can also show that a mu hat is a consistent estimate of mu, since when n goes to infinity, this mu hat will converge to mu in terms of probability. Now, the covariance matrix of this sigma hat for this guy, you can show that if you take the expectation, it equals to n minus 1 divided by n. That is not the same as sigma. Okay, therefore, you say that sigma hat is a biased estimate of your sigma. To be unbiased, you want to make sure that the expectation of the estimator equals to the true estimator. Okay, however, this covariance matrix is consistent because as n goes to infinity, this sigma hat will converge to sigma. You just set n equals to infinity, then these two ratios will go to 1. Okay, now you can make sigma into unbiased by defining this 1 over n minus 1. Right, so that is the difference between this equation and that equation. Here you use 1 over n. There you use 1 over n minus 1. You can show that expectation of this sigma hat is sigma for this guy, okay, not that one. Okay, so the importance, the significance of this n minus 1 versus n, that's negligible when your n is big. It becomes influential when your n is small. Okay, so if you're interested in knowing where does this n minus 1 business versus n business come from, here is a derivation, which I think is not very interesting, so I'm gonna let you read it by yourself. But what you can do is that you can work on the 1D case, and then writing down the variance of this quantity, and then you can evaluate this expectation of the variance with some algebra. This is just calculation of all these cross terms, square terms, and then do some magic here, and then you can get n minus 1 divided by n. Okay. Unfortunately, that's just no intuition. Okay, to me. Okay, this is just tedious linear algebra, not too tedious. Yes, okay, no intuition behind all these. Okay, as far as this n minus 1 divided by n is concerned, it just comes out from the math. All right. Okay, so this is a little bit more interesting. Now, suppose you have find the model parameters. Okay, so now you have found the model parameters, and then if you have a training data set, what you would do is that okay, so you start with the training data set. You first partition it into two classes, class 1 and class 2, and then for each class, you find the model parameter using the maximum likelihood estimations. Okay, so you need to do that because this is the training procedure of your problem. Two classes, so you learn mu1 sigma 1, mu2 sigma 2, each one for the class. In homework number 3, you will have opportunity to practice this, that you will be given a data set that contains two classes of data points, and then you want to learn the mean vector, the covariance matrix of the two classes. So you have mu1 sigma 1, mu2 sigma 2, and then you need to construct a decision boundary based on the model parameters. So what would you do is that you want to construct this discriminant function. Okay? Because eventually what you will do is you will want to construct this hypothesis, which is either yes or no for the testing data that you give me. So how do you do that? It would be 1 when the discriminant function is positive, 0 when the discriminant function is negative, and therefore everything you need to do is to construct this discriminant function. This discriminant function has this form for Gaussian model. Now, the model is the model that you use for inference, not necessarily the model that is underlying. Okay, it could happen that there's a mismatch, but don't worry about that. We just focus on the inference model, which is a Gaussian in this case. So now you have a Gaussian model, then you go back to the previous lectures. There are formulas for this W1 matrix, W1, W2 vectors, and also the W10, W20, these are the offsets. So going back 2 lectures ago, we have formula telling you how to set up all these. Okay, so these would be a function of the mu1 sigma 1, mu2 sigma 2. Okay, so you plug all these numbers into here, you get a discriminant function. And then once you have a new testing data point, you check whether this is on the positive side or on the negative side, then you make a decision. Okay. All right, so this is the routine for doing the classification. Okay, so a very important question that we want to ask is how well does this maximum likelihood perform? Okay, when will it fail? So suppose that you have a data set that contains n points, and then you have estimated mu by solving the maximum likelihood problem. And so now you have an estimate of mu hat equals to the sample mean. Now you ask, how good is your estimate? Okay, how good is your estimate? What do you do? Well, you look at this quantity. This is a random vector. Okay, if you go to the 1D case, it will be a random variable. Now, mu hat is a random variable, so you can ask, what is the expectation of this random variable? Okay, random variable always has a mean. Okay, now you ask, how far is my random variable? It has random fluctuations compared to the true mean. Okay, so that will measure the deviation. I ask, this is an event, right? I want to ask what is the probability that this will be big. Okay, so you ask what is the probability that this is bigger than certain epsilon that I'm choosing. Okay, so if you want to view it, this is what is the probability of having a bad event, right? If you can quantify this probability, you are sort of telling me how good is my estimator, right? There's no other ways that you can quantify. Well, no, okay. You can also measure the mu hat minus expectation of mu hat. You can do this square. Okay, you can also take the expectation, but there's not too much difference between these two. Okay. So let's look at this quantity. This is the probability, right? So you want to quantify the probability of getting this bad event. Okay. Now, how to do that? Well, we will come to this point later in the semester. Okay. There is a set of probability tools, which is called the probability inequalities, that can help you analyze bad events like these. Okay. What do you want? You want the probability of these bad events to be well controlled. Okay, and one of the results that comes from all these studies is called the Houghton inequality. What it shows is that this bad events is upper bounded by this magical quantity is exponential function of minus epsilon squared times n. Now you can keep your n, you can keep your epsilon to be 0.1, 0.01. That's a number that you can choose. However, as n goes to infinity, what happens to this exponential term? That will go to 0 extremely fast. Okay, that means if I have more and more samples, then the probability that this will to live nearby your true mean is very, very high. Okay, so that provides you a very, very concrete way, a precise way of quantifying how well your estimate is relative to the number of training samples. Okay. Again, we'll come back to this probability inequality later in the semester. I will here just mention that the existence of this thing so that you can start to read some textbooks to prepare yourself for the upcoming lectures. All right. All right. So, let me give you a 1-minute overview of what we are going to do next time, and then I will stop. So far, we have talked about the frequentist approach by treating your parameter theta as a fixed unknown quantity. Okay, there is no underlying distribution of the theta. However, in the next lecture, we are going to look at this thing called the Bayesian approach, where you assume that your mu is no longer a fixed quantity. It has its own distribution. So there is a hyper prior for your parameter. Okay, so there is a prior for your parameter. So then you need to worry about this p theta. So I will come back to this example later on. But what I want to show you is this. There will be you will see the slide again next lecture. Then there will be a distribution of the mu. Okay, so the mu is no longer just a delta function, but now you have a distribution of the mu. Okay, and so if you have a mu here, then if you have a prior of the theta, then what you would do is that it's actually not too different from the maximum likelihood. You go through all these derivations, which we'll go over next time. You see that in this negative likelihood term, you will still have the likelihood function. However, you will add one more term. It's called the prior distribution, which is exactly the same as the regularization function that we learned in lecture number 1 or 2. Okay, so this sort of bridge the gap from all this probabilistic approach to the deterministic approach that we have learned so far for the pipeline, for the optimization. It comes to here. Okay, so we'll pick up from this point. I will go back a few slides back next time to motivate the need of doing the Bayesian estimation when there is a prior. All right, so I will see you guys next time.